which include almost 50 events of coalescing black holes. And it's now crucial to understand what is the physical origin behind these coalescing black holes. And up to now in the literature, two main formation scenarios were proposed for these black holes. And those are the astrophysical black holes and the primordial black holes. So astrophysical black holes form from the collapse of a star under gravity with a mass which is bigger than the Chandrasekhar mass, that is about the solar masses. While primordial black holes may form in the very early universe from the collapse of large inhomogeneities, and those can span a much bigger range of masses with a lower cutoff obtained by requiring that they are not evaporated until today due to Hawking radiation. Now, these two different formation scenarios, of course, will lead to different predictions for the black hole features, which are their masses, their spins, and also their merger rate, which in turn will impact what we see at the present experiments. So in particular, at the gravitational wave experiment, what we see is the gravitational waveform, which is determined at the leading order in perturbation theory by the chirp mass, which is a combination of the primary and secondary component masses of the binary. While at next to leading order, it depends on the mass ratio, which is the ratio between the secondary and lighter component with respect to the primary and the heavier. And also it depends on the effective binary spin, which is basically a projection onto the orbital angular momentum of the individual spins of the binary black holes weighted by their masses. So it's crucial to understand how these two scenarios will impact on the waveform. The interest in primordial black holes also arises because they behave on cosmological scales like a cold and collisionless fluid, and as such, they can represent a fraction of the dark matter in the universe. So, for example, in this plot, you can see on the horizontal axis the PBH masses, while on the vertical axis you can see the present abundance of primordial black holes in the universe normalized to the dark matter one in a parameter which is called FPBH. And there are, of course, several observational constraints on the PBH abundance, which come from several phenomena. So, for example, for very small masses, one has constraints from Hawking radiation, while for larger masses, there are constraints from microlensing events. And on the right of this plot, there are also constraints from gravitational waves observation, so from the LIGO Virgo data, and also from accretion at very high redshift, which may impact on the CMB anisotropies, and therefore constraints from Planck data. Now, as you can see from this plot, there is a wide region in which primordial black holes may account for the full dark matter in the universe. But today I will focus mainly in the region around the solar masses or larger values, so related to the bounds by gravitational waves. And the interest in primordial black holes also arises because they can help in filling the so-called astrophysical mass gap, since we know that there is a sort of gap predicted by the theory for astrophysical black holes between 50 and 130 solar masses, which arise because if a star is massive enough, basically there may be a production of electron-positron pairs which reduce the pressure inside the star, which starts collapsing. And basically, after this collapse, there are some losses of masses due to the burning of carbon, which may lead to ejection of matter. And therefore, the resulting black hole is expected to be lighter. But of course, this kind of phenomena does not affect primordial black holes, whose masses can span a much bigger range. So this was a sort of motivation for my talk. So today I will talk about primordial black holes and gravitational wave events. And at first I will discuss the PBH formation. and see later how they evolve during the cosmological history. Then I will discuss how the PBH model will confront with the second transient catalog. And finally, analyze a possible mixed scenario in which a binary is composed by a primordial and an astrophysical black hole. So let me start with the PBH formation. And we will consider the most common formation scenario in which primordial black holes are basically originated from overdensities in the radiation fluid created by perturbations during inflation, which are transferred thanks to the reheating phase. And basically, a primordial black holes can actually form if these overdensities are sizable enough, which means that their density in contrast has to be larger than a certain threshold, which is found numerically. And then a primordial black holes can form when this perturbation at horizon crossing is larger than this threshold. Of course, this threshold will depend on the curvature power spectrum from which a perturbation are originated. And there are several important GR numerical simulations which have tried to find this value. And we also provided recently a very simple prescription based on this simulation to compute the threshold from a given shape of the power spectrum. Now, the power spectrum is also crucial because it determines the initial mass function for the primordial black holes. And a very common and useful parameterization of this mass function is provided by the log-normal shape, which usually arises in scenarios in which the power spectrum has a symmetric peak. And it is described by two main parameters that are its central mass scale, nc, and its width, sigma. So this is the first kind of property of primordial black holes at formation. And the second is related to the primordial black hole spin. So as already stated before, basically primordial black holes originate from local maxima of the radiation overdensity field. And according to the known peak theory, those peaks are expected to be basically spherical. However, there might be asphericities during the collapse, which may lead to the formation of a spin from the consequent black hole due to the action of torques originated from the surrounding perturbation. However, since we are in radiation domination, the time of collapse is expected to be very small due to the presence of the radiation pressure, and therefore the action of these torques is actually quite limited in time. And one can study, using the formalism of peak theory, what is the probability distribution of the primordial black hole spin at formation, and found that basically if there is a slightly non-spherical collapse, then primordial black holes are expected to be basically no spinning, or with a spin below the percent level, modulo a correction factor which depends on the shape of the density power spectrum. So this is the second feature of primordial black holes at formation. But of course, primordial black holes do evolve during their cosmological history. And there are several phenomena which may affect their evolution. So those are primordial black hole accretion that I will describe in a moment, and also possible mergings. So I will denote here as primary mergings those that basically happen very close to us, so those that we see at the present gravitational wave experiment. But there are also basically secondary merging, in which one of the components actually arises from a previous merger. However, for the LIGO Virgo range of masses that I will consider in this seminar, basically the probability to have a secondary merging is found to be negligible. So we will neglect it in the following, and just show how accretion and primary mergings will affect the primordial black hole properties and see their impact at the present experiments. So let's start with accretion. So primordial black holes may actually experience accretion during the cosmological history in two possibilities. So the first is onto individual primordial black holes, And the second is onto primordial black hole binaries. And those will have an impact on the PBH masses and spins. So let's start with accretion onto individual primordial black holes. So the basic picture is that you have a primordial black hole which is moving with a certain velocity in the surrounding intergalactic medium. And basically it may accrete baryonic particles which are in the region around it, in a region which is usually called as the boundary radius, that is determined by the PBH masses and effective velocity. And a very known parameterization for the mass accretion rate is provided by the Bondi oil formula that I'm showing here in this slide, in which the mass accretion rate depends on the PBH masses and velocities, on the number density of the surrounding gas, and also on an accretion parameter, lambda, which captures several important effects like the Hubble expansion, the gas viscosity, also the coupling to the CMB radiation. So the important point is that during the cosmological history, basically primordial black holes may undergo epochs of efficient accretion if they are massive enough. But there is another important ingredient which has to be taken into account, which is the formation of a dark halo. Because if primordial black holes do not represent the full dark matter in the universe, we expect that there is another dark matter component, which is dominant, that may actually create a halo around the given primordial black holes, with a mass which of course will increase with time. And the main effect of this halo is actually to act as a catalyst for the baryonic accretion rate. So basically its main effect is to enhance the accretion rate onto the primordial black holes. Then we can move to the description of accretion onto binary primordial black holes. And here the situation is a bit more complex because one has not only processes onto the individual primordial black holes, so on locally, but also onto the whole binary. But as the same major axis of the binary is smaller than the binary boundary radius, basically one can describe the accretion flow onto the whole system, and then compute the individual accretion rate onto the single primordial black holes, which of course will depend on the characteristic masses, the velocities in the binary, and also on the density around them. And after some simplification, one gets this two expression for the individual accretion rates in terms of the mass ratio of the binary. And an interesting feature which arises in this kind of modeling is that the smaller primordial black hole in the binary always experiences a larger relative accretion rate with respect to the primary component. And this happens because it sees the accretion flow also due to the presence of the primary component and heavier. Now, accretion will continue until we reach redshift around 10 or so. So basically, until we reach the onset of structure formation and reionization. Since around these epochs, basically there is an increase in the temperature of the surrounding medium, and also due to the increase of the velocities of the primordial black holes which fall within the viralized structure. And therefore, the accretion rate is expected to diminish a lot. And in order to account for this decrease in the accretion's efficiency, we have introduced a parameter, which we call the cutoff redshift, zeta cutoff, after which basically we neglect accretion. Of course, the value of this cutoff is actually quite unconstrained because there are several uncertainties in the accretion model, due, for example, to the details of structure formation, or also due to feedbacks of local, global, and mechanical type, and also to X-ray preheating, which of course may change the point at which this suppression occurs. And therefore, we have decided to let this cutoff to vary in order to account for this efficiency. And now, this was a sort of introduction to the modeling of accretion. Now we can see what are the consequences for the primordial black hole masses and spins. So the first consequence is, of course, on the mass function, which evolves as accretion takes place. So in this plot, you can see on the vertical axis the mass function in terms of the mass, and the green curve basically is the one at formation by fixing the central scale of the mass function and the initial width. And as accretion takes place, the main effect is that the mass function gets broader with a tail at larger masses when accretion, of course, is more relevant. And as you can see, as the cutoff is lowered, so accretion lasts longer, basically the main effect is that the tail will get to higher values, of course. And the second prediction of accretion is onto the mass ratio of the binary system, which, since the secondary component experiences a relatively larger accretion rate with respect to the primary, basically is pushed towards unity. And in this plot, you can see the evolution of the mass ratio by fixing the initial masses of the primordial black holes in the binary in terms of redshift, or if you want, of time. And as you can see, basically, the mass ratio will grow towards unity. So asymmetrical binaries tend with time to become symmetrical as accretion takes place. And the third consequence of accretion is related to the evolution of the spins. So this happens because basically the accretion rate and the geometry of the accretion flow onto the binary are actually highly connected. And in particular, the baryonic particles which are falling towards the primordial black holes may actually carry an angular momentum, which may create an accretion disk around the primordial black hole if the accretion is efficient. And once this accretion disk is formed, thin, basically it may lead to a transfer of angular momentum from the baryonic particles in the disk towards the primordial black holes. And using the geodesic model by Bartin et al., one can compute the spin evolution in terms of the mass evolution, which of course is dictated by accretion. And in this plot, we show the evolution of the primary spin in blue and the secondary spin in red in terms of redshift of time. And as you can see, we start from basically very small values of the spins, since at formation, primordial black holes are basically no spinning. And as time goes, the spins will be pushed towards extremality, with the secondary spin that is always larger than the primary. And again, this is a consequence of the fact that the secondary component accretes more relatively with respect to the primary. Now that we have a prediction for the individual spins in the binary, we can also provide a prediction for the effective binary spin. So in this plot, we show basically the distributions of the chi effective respect to the primary component masses and fixing the mass ratio of the binary system to unity. So if we look at basically very small masses, as you can see, the distributions are peaked around 0. And this is due to the fact that for small masses, accretion is not relevant, and therefore the spins are those at formation, so basically negligible. But as the masses are higher, then accretion is more relevant, and therefore the individual spins will grow with time. And since their direction with respect to the orbital angular momentum are actually randomly distributed on the two spheres, basically this results in a distribution in the chi effective, which gets a spread around 0, with a transition from no spinning to spinning, which will depend on the cutoff redshift. So as the cutoff, for example, is larger, it means that accretion lasts for a shorter period, so it's less efficient. And therefore, the transition to spinning case will only arise for larger masses. So there is a correlation basically between low masses and low spin and high masses and high spin. So this concludes more the prediction for the primordial black hole masses and spins. And now we can see the primordial black hole merger rate and how accretion impacts on that. So since we are assuming that the curvature perturbation which originate the primordial black holes are Gaussian, basically primordial black holes at formation follow a Poisson distribution. And it may happen that around the matter radiation equality, a certain two-body system may decouple from the Hubble flow. So one can compute the probability that a two-body system may actually decouple, form a binary, which with time will emit gravitational waves and finally merge. And in this very complicated expression, we provide the primordial black hole merger rate, which depends on the, of course, the masses of the primordial black holes in the binary, on the mass function, on the PVH abundance, and on a suppression factor, S, which takes into account the probability that a given binary system gets disrupted by other primordial black hole or from other matter perturbations. Now, the main effect of accretion onto a given binary system is to make it harder, so it shrinks its semi-major axis, and therefore it enhances the merger rate. So one can understand this final sentence because the accretion time scale, which is about the salpeter time scale, is much shorter than the time scale which governs emission of gravitational waves. So it means that before the cutoff redshift, so when accretion is present, it is accretion the main phenomena which drives the spiral of the binary. So we expect that the binary, basically the individual masses and spins of the component in the binary will, of course, increase due to accretion. And the binary system will basically get harder. And once we reach the cutoff, then accretion is neglected. So we have a new binary, which is harder and heavier. And since it is harder and heavier, basically the time scale of coalescence now is of course diminished due to this effect, which results in an increase of the merger rate. So now this concludes the modeling part of primordial black holes formation and evolution. So I will pause here if you have some question before I'm going to the second part of my talk, which basically is the confront with the second catalog. Okay, so I will go on. So as you know, recently the second catalog of gravitational waves has been released by the LIGO Virgo collaboration. And the most important highlights of this catalog was that basically almost all the events have been found to have a mass ratio posterior, which is compatible with unity. And also that almost 10 spinning events were found in the catalog with a K-effective posterior, which is actually displaced from zero. Now, what we did was that we performed an analysis considering these events as primordial black holes coalescing events. But we've decided to not consider some events of this catalog, which are those with very high false alarm rate, and also a couple of events which can possibly represent a neutron star. So in order also to follow the population paper by LIGO, we have chosen to not consider them in our analysis. So what we did was to consider all the other events to be primordial and perform a hierarchical Bayesian inference in order to find what are the population hyperparameters for the PVH model which best fit the data. So these population hyperparameters are described by a vector lambda and are the central scale of the initial mass function, MC, its width, sigma, the PVH abundance, and the cutoff redshift. And basically, with this inference, we have computed the posterior population for these hyperparameters, which is obtained by integrating over the event parameters, which are the binary masses, K-effective, and the redshift of merger, of the product between the event likelihood and the population likelihood, which is basically a sort of prior which captures, given a set of hyperparameters, the event parameters. And the result is multiplied by a population priors, which is assumed to be uniform. And the result of this inference is provided by this corner plot, in which we see all the possible correlation between the set of hyperparameters considered. But if we just focus on the marginalized posterior, so we can consider what are the values at which these posteriors are basically picked. And those are reported in this box. So the initial mass function is picked around 16 solar masses, and it is quite broad. So its width is about 0.6 or so. Then we have found that in order to account for all these events to be primordial, the PBH abundance has to be around 10 to the minus 3 or so. So in order to explain these events, primordial black holes cannot represent the full dark matter. And finally, we've also found a preference for moderate accretion, so zeta cutoff around 20. Now, once found this best fit population, we want to see if it is allowed by present observational constraints, and then deduce the main properties of this population. So we are now to see if this population basically is allowed or ruled out by the present constraints. So in this very important plot, we show on the vertical axis the PBH abundance at present time with respect to the mean mass of the mass function. And we have fixed in this plot the cutoff redshift and the width to the values found by the best fit analysis. And as you can see, there are a lot of constraints in this plot that I will just sketch very fast. So there are constraints from microlensing event in green. Then there are constraints from X-ray and X-ray binaries emission due to accretion of primordial black holes at low redshift. Then there are constraints from Planck data, since primordial black holes may experience accretion at very high redshift between 300 and 600. And this accretion will basically lead to the emission of radiation that may impact onto the CMB temperature and polarization anisotropies, which are constrained by the Planck data. But of course, these constraints will depend on the geometry of the accretion flow, which is assumed. And these constraints are basically, the geometry can be a disk geometry or a spherical. But since we are at very high redshift, the formation of a disk is actually quite improbable. So the most probable scenario is to have a spherical geometry, which is the solid red line. And finally, we also constraints from nanograv, since we are considering a formation of primordial black holes thanks to curvature perturbation, which a second order in perturbation theory will also generate a stochastic gravitational wave background, which may be detected by the nanograv experiment. And in there, the constraint is the black line. So as you can see, the star, which is the point which best fit the data, is actually allowed by present constraints. Let me also stress for this comparison that basically the clustering is not affecting these constraints. And one can easily understand that because basing on the results of an n-body simulation performed by Imma and Aliamud last year, basically primordial black holes for very small abundance, so in our case for around 10 to the minus 3, basically are found to be isolated. And therefore, for low abundance, clustering is negligible, and the constraints are not affected by it. Of course, the situation may change for larger abundance, and we have also done a paper about that I would be happy to describe if you are interested after the talk. So we have said that the constraints perfectly allows this scenario, and now we want to see what are the predictions for the population that we are considering. So at first, we can describe the mass distribution. So on the left, we show the marginalized posterior for the primary component masses. And as you can see, this curve basically has a tail which reaches very large masses, around 80 solar masses or so. So it falls within the astrophysical mass gap. So events like GW 190521, in which at least one of the components lies within the mass gap, are expected from this primordial black hole population that we found, with a rate which is consistent with the observation rate. While in the plot on the right, we show the posterior for the mass ratio, which, as you can see, peaks around 0.5 or so. So it is different from unity. And this is due to the fact that the mass function width is found to be quite large at formation, and also due to the preferred high values for the cutoff redshift found by the analysis. Then we can study the merger rate evolution. So in this plot, we show basically the merger rate in terms of redshift. And the blue line indicates the primordial black hole merger rate, while the red line indicates the merger rate evolution found by the collaboration, assuming a power law model. And as you can see, the two rates are compatible with each other. And finally, we can also describe the effective spin and superimpose on our previous prediction the data, which are shown by this let's say, star. And basically, as you can see, the presence of several spinning events in the catalog basically leads to a preference towards smaller values of the cutoff. Since in order to basically describe these events, which were found to be spinning, the only way for primordial black holes to do so is to let them experience a phase of accretion in order for their spins to grow. So this concludes a bit the description for the population distributions, and now we can give some future prospects about in this line of research. So of course it would be nice to improve the modeling of accretion onto primordial black holes, especially with the presence of a secondary dark matter component, which is responsible for the formation of the halo. Then it's also important to study observational gravitational waves at very high redshift, thanks to future experiments like Einstein Telescope or Cosmic Explorer, which are able to distinguish potentially primordial black holes from astrophysical black holes at this given high redshift. And then it would be nice also to compare the primordial scenario with the astrophysical models, which may explain these events. The most known scenarios are those from isolated formation in galactic field, or from dynamical formation in high density environments like clusters, or also population tree. And finally, one can also study mixed population between astrophysical and primordial black holes. And along this last point, we have recently made some efforts in order to study this kind of scenarios that I would like to describe in the last part of my talk. But again, I will pause here if you have some question about the second part that I will be happy to answer now. Okay, so if not, I will go to the last part, so the mixed scenario. So here the idea was to explain events like GW 190521, in which the primary component mass was found to be around 80 solar masses, so well within the astrophysical mass gap, and the lighter secondary component to be around 66 solar masses, and try to explain this kind of events as the merger of a primordial black hole and an astrophysical black hole, in which the primordial black holes represents the events in the mass gap, and the other object is the astrophysical black hole. Of course, to lead to the formation of this kind of mixed binaries, The only possible way is to basically use dynamical encounters in environments which have very large density. So for example, in Milky Way globular clusters. And for this kind of clusters, basically, since the black holes are heavier, they tend to segregate towards the core, towards the center of the clusters, while stars will move, since they are lighter, within the cluster itself. And in order to simplify a bit the description of this kind of scenario, we have chosen to assume a bimodal mass function for the astrophysical black holes, with a dominant peak around 10 solar masses and a low peak around 60 solar masses, compatible with the secondary component of GW and TINO 521. While for the primordial black holes, we have assumed a monochromatic distribution around 80 solar masses. Now, of course, there are several unknowns in this kind of scenarios. For example, one of them is the fraction of retained astrophysical black holes in the cluster. Since at formation, those astrophysical black holes may receive natal kicks due to from previous supernova, which may basically lead to the ejection of the astrophysical black holes from the cluster. So we have chosen to parameterize this fraction in terms of a kick velocity, which we have run on to account for this effect. And another unknown is basically PBH local overdensity in the globular cluster, which is expressed as a fraction F80 of this overdensity in terms of the baryonic overdensity in the cluster. Of course, one can try to connect this fraction in terms of the global PBH abundance, FPBH, modulo some correction factor overall, which may depend on the given clusters, which may reach even a couple of orders of magnitude larger. Of course, there are already stringent bounds on the PBH abundance. For example, the PBH abundance has to be smaller than 10 to minus 5 in order for PBH-PBH merger not to overcome this kind of scenarios. So this F80 parameter will run with values around 10 to minus 4 or so. And now I'm going to describe 3 possible mechanisms which could explain this kind of events. So the first is the direct capture. So a picture is that you have an astrophysical black hole and a primordial black holes, which may basically move very close to each other. And since they are so close, basically there is an emission of gravitational waves, which leads to the formation of a binary, which will later merge due to emission of gravitational waves. And in this plot, we show on the vertical axis the merger rate of this direct capture channel in terms of the kick velocity by fixing this PBH overdensity fraction to some reasonable value, as explained before. And as you can see, the rate for this channel is found to be well below the observed value for the considered event. So that capture cannot explain the origin of the events of this kind. The second scenario that we studied is the three-body induced. So we have a very similar picture to the one of before. So we have astrophysical and primordial black holes which pass close to each other, but not so close to give a direct capture channel. However, the presence of lighter objects in the vicinity of this region, for example, stars, may lead to the formation of a binary with, of course, some efficiency related to the dynamics of the velocities, the masses on the object. But once this binary is formed, it's found to be quite soft, so to have quite a large same major axis. And in order for this binary to basically harden and merge, the presence of several lighter objects like star in the dense environment may actually lead to interaction of the binary with these lighter objects that makes the binary to harder, until emission of gravitational waves starts to get relevant. And therefore, one can compute the merger rate for this channel, which is shown in this plot. But again, unfortunately, this merger rate is found to be below the observed value for GW 190521. So even this scenario cannot explain this kind of event. And the last mechanism that we studied is what we called a catalysis. So basically, we have an initial population of 10 black hole binaries, which may experience a chain of binary single and binary-binary exchanges with the other 60 astrophysical black holes and 80 primordial black holes in the dense environment, which leads to the production of several binaries. And among those, there is also the formation of 86 binaries, which is the one that we are considering in this seminar. And this last binary merger rate is shown in this plot by the black dashed line, which has a given Siam band around it, due to the fact that we are averaging over Milky Way globular clusters, which experience, of course, many different number density in the local universe. So we are accounting for the uncertainties in this number density in this Siam band around the black dashed line, which has to be compared with a band. And as you can see, for example, in the central plot, it may lie within the observed value. So this kind of channel may actually predict a merger rate that may be compatible with the observed value for 190521. So let me conclude. So we have studied the importance of accretion for primordial black holes that predicts a redshift-dependent correlation between high spins, high masses, and symmetrical binaries, with the secondary component that always spins faster than the primary. And then we have tried to compare the PBH model with the data from the second transient catalog, and seeing that the data are compatible with the hypothesis that almost all of these events are primordial, and this is also allowed by present observational constraints. And finally, we have studied the possibility to explain GW 190521, which is one of the mass gap events found in the catalog, that can be described or as a primordial black hole binary, or also as a mixed primordial astrophysical binary following the catalysis mechanism. So with this I conclude, and thank you for your attention.
Thank you very much, Valerio. We now have time for questions. Who wants to go first? So just unmute yourself or raise your hand. Okay. Archer, do you have questions?
Yeah, I have a question. First of all, Valerio, thank you very much for a nice talk. It was very illuminating. Learned a lot. Now, I have a few questions, but one of the things the question is that how this results, the matching with the catalog, for example, the theoretical predictions are robust against the production mechanism of the black hole. So, for example, if I assume that they're produced through the the bubble collisions, for example, in first order phase transition, is that change something? I mean, the mass function and the spin and so on. Have you thought about that?
Okay. So yeah, of course, our results are basically considering a given mass function, which is a known parameterization for example, symmetric peaks in the cubic power spectrum. And then we're trying to best fit this mass function in terms of its free parameters, which are its width and central mass scale. Now, if you consider other formation scenarios like bubble collision, this may lead to different prediction for the mass function or also for the spins. And so one has to dedicate, I think, an analysis to that in order to see if it's compatible or not. Probably there are some free parameters in this kind of formation scenarios, over which you can try to fix in order to explain the data. But I don't know if there are some papers which, for example, explain how the spins is computed from these formation scenarios. So it would be nice to study those kind of mechanisms, yes.
Right. So I think you are right. I mean, maybe the theoretical prediction, you know, the uncertainties are still large to discriminate actually these two scenarios. Would have been very nice actually. But I don't know whether anyone studied, you know, the study you performed with respect to other production mechanisms. Have you aware of those?
No, I don't know. For example, for the spin from bubble collision, I don't know if there is a paper which, for example, studies that. It would be interesting because, for example, in the scenario from Kuboto perturbation, there the spin we have studied, and there is a prediction for very small spins. Now, from bubble, I don't know if there are papers, but to my knowledge, there are not about that. Yeah, it would be for sure interesting because maybe if the spin is found to be higher, of course, there may be a difference in the relation between, for example, low masses, low spin. This correlation that we found, it may change if this bubble will lead to a primordial black hole spin. But I don't have an answer to that. I mean, it deserves further study for sure.
Thank you.
Further questions? Could you go to the plot with the constraints?
Yes.
Which you showed where you...
This one?
Yeah, this one.
Yes.
So I'm not working on primordial black holes. I'm just interested. So what future experiments how would they constrain that parameter space more?
You mean future experiment of gravitational waves?
Yeah. So which future experiments would basically cut into that parameter space more? So which could then test that?
So of course, I mean, the constraints which are present here are basically constraints from independent, like accretion, microlensing, and so on. If you are considering, for example, 3G radiation wave experiments, there you will be able to study, for example, the merge of primordial black holes at higher redshift. So if you don't see anything there, it may change since we have a clear prediction for the primordial black hole merger rate with the redshift, which is given by this this line here, for example. You have a sort of prediction for what you expect from at a higher redshift, for example, from Einstein telescope, and see, for example, if you see some events there, how much of them do you see, and see if this scenario that you have seen at the, for example, LIGO experiment matches what you see at the Einstein telescope or not. So with this kind of analysis, by assuming that all the events are primordial, we have fixed, if you want, the mass function, of course, and for example, the cutoff redshift. And then you want to see if this kind of mass function predicts some events at higher redshift, which are compatible or not with what you see at Einstein telescope. And it may help in discriminating if this scenario is actually allowed or not. For example, it may be that only a fraction of these events are actually primordial, that their fraction is astrophysical. So it may change the mass function that you need in order to explain that. So yeah, of course, it's an interesting question, and it's a further study to see what is the prediction at a higher redshift.
Oh, okay, so it's not clear yet where it would cut into the parameter space, or where it would...
Yeah, of course, because here, these are, for example, this star is obtained for this analysis with this assumption, and trying to best fit the data that we see at this at the low redshift, of course. And probably, of course, since these constraints also depends on the mass function that you are considering, the prediction of 3G experiments may change, because if we change the mass function, also the constraints the shape of the constraints may change. So yeah.
True. One more thing, follow up on that one. So there was on the previous slide also there were distributions for the points, right? That was just the best fit point.
You
how
mean
large
here?
would be the?
Sorry, you mean in this slide?
Yeah, this slide. Okay. So if I then look at the other slide over there, I just wanted to get a feeling for how large the range would be, where the whatever 1 sigma or whatever confidence level you draw.
You mean around each of the best fit values?
Yes, yeah.
Yeah, there are, for example, for the central mass scale, around 2 solar masses as a width, more or less, for the 1 sigma and so on. Yes.
Okay, thanks.
You're welcome.
Other questions? Well, if there are no more questions at the moment, then let's thank Valerio once more for a very interesting and illuminating talk. Thank you very much.
Thank you so much. Thank you for the invitation.
Yeah. So Archel, maybe so you had that paper on primordial black holes. So how does that fit in there? That was a different type of primordial black hole, or different?
Which paper are you talking about?
Archel